All right, welcome to topic 7.7. So initially, this is not where I was planning on starting this week, but I got thinking more about what would be useful for making the topics we were going to work on this week a little bit more accessible to you guys. And so I thought this kind of review of old with new might be kind of useful. So we're going to take what we've done with balancing equations and we're going to add some parts to it with translating equations today. And this can become a little bit of a time-consuming process depending on how much of your chemical naming you remember. So before you dive too far in, you're going to want a periodic table and a polyatomic list for the examples that are going to be coming. So when we take a look at this, we know some of the symbols that we use in the equation. We've done the arrow and plus sign. And so we know that a plus sign is like and. It just separates multiple reactants from one another, multiple symbols, so we know what is what. The arrow indicates yields, so we know where the reactants start and where the products start. The thing that we're going to introduce today is the whole idea of we can indicate states of matter, so solid, liquid, gas, and then what's called aqueous. So when we write these in, these will be shown as subscripts. I'll explain that more as we get to the examples. Obviously, an S stands for solid. A lot of times liquid, we use like a lowercase l with the loop there, so we know that we're describing an L there. But otherwise, knowing that those represent states of matter, that's liquid, and then G for gas. Aqueous is any time that we make something in solution. So if you've made salt water that you've gargled before, you have made an aqueous solution. You took salt, dissolved it in water, and it broke apart into sodium cations and chlorine anions. And so when you take salt and put it into water, you don't change those salt ions or the salt compound itself into the liquid state, but rather the aqueous state. Down here, we can do a couple of things with our arrows. So if we put a delta sign, that triangle above the arrow, that tells us heat is needed. A lot of times with synthesis and decomposition reactions, in order for them to occur, heat is needed in order to get the reaction kind of started. And then from there, we have a catalyst. You guys talked about catalysts in biology last year. A catalyst is basically a binding site for reactions. It's not a reactant, it's not a product, it's not consumed up within the equation or within the reaction, but rather speeds up the reaction because it lowers the activation energy. So you guys may remember doing a lab with liver last year in biology, and that was showing the use of a catalyst with helping enzymes. So from there, we're going to work on these 4 examples. So what I have is, before we can really get started, I want to include one thing that's going to help us with this bottom half. So one thing I want to mention is anytime we have elements on their own, they typically are what we call monoatomic. So most of the elements are monoatomic. So like iron is Fe, calcium is Ca, let's see here, phosphorus is just P. So when we describe most elements, it's just their symbol. Now, there's 7 elements specifically that are called diatomics, and this is word, I should say, that I have brought up off and on throughout the entire year. So diatomics, there's a way to remember that, and that's using the acronym Hoffenkleiber. So that stands for the 7 elements that are not monatomic. Every other element is. So these 7 include hydrogen. So when we write hydrogen, we write H2, oxygen, O2, fluorine, F2, iodine, I2, nitrogen, N2, Cl2, and Br2. So these are the 7 elements that do not exist on their own in nature, but rather in the diatomic state. If it's not one of these 7, we write just the symbol. Okay, like I said, that's going to be important for these examples. Okay, speaking of which, we're going to swap gears and start translating using that information we have with what's going to be a little bit new here. So here we have copper metal is heated with oxygen and it gives solid copper 2 oxide. Okay, and so the first thing that you want to make sure you understand when you take a look at this is what is the reactant versus what is the product. Okay, so I can see that copper metal is heated with oxygen and it gives. So that means that these 2 things are our starting material or the reactants. So what I'm going to do is start translating this into actual symbols like you kind of do in practice with foreign languages. So copper is not one of the 7 diatomics, it's a monoatomic. That means its symbol is simply just Cu. It says that it's metal. That tells me it's a solid state. When you write in your state of matter, you write it as a subscript in parentheses so you don't mix it up as part of a polyatomic or as the element sulfur. Okay? And it says it is heated with, so I know that it had to be heated with something, and that's with oxygen. Oxygen, however, is one of the 7 diatomics. When we write its formula, it is O2. Oxygen at room temperature is a gas. It tells me it's heated, so I'm going to put the delta symbol over the arrow telling that heat was supplied. And this is the part where things change a little bit. We're going to take what we've done and blend in some things new. So we have copper 2 oxide. We spent a whole unit on naming. Copper 2, that Roman numeral tells me copper is a +2 cation. And I know oxide, using my periodic table, is just oxygen. Oxygen is a -2 charge. Notice, diatomics, Hoffman-Kleibers, that applies only to the element when it's 100% on its own, not when it's in compounds. So when I cross my charges here and simplify them, my formula is CuO. So what I'm going to put here is CuO, and it tells me it's a solid. Now we're to where and what we've been doing all along. We're going to balance it. When I take a look, my copper are balanced right now with 1 and 1. Oxygen, I have 2 and 1. So I'm going to go ahead and put a coefficient 2 on the product side. But in doing so, that changes the copper, and a 2 is needed here. The last thing, just as a review for our quiz on Tuesday, is the product type. This is synthesis. We can see that elements are combined into one product. Okay? So now for example B, and I'm going to move my camera real quick. In B, we have mercury 2 nitrate. Okay, so with that, I have, let's see, I might actually just change my piece of paper so that way I for sure stay on the camera. Okay, so we have mercury 2 nitrate. So I'm going to go ahead and just start with translating these formulas from the name. So I know that when I see a Roman numeral, like up above, the Roman numeral is the charge of the metal. And I'm going to pick a pen that's a little bit better to see than this orange thing here. Okay, so mercury 2 nitrate. So mercury. So mercury is going to be a Roman numeral 2 because of the Roman numeral 2 plus 2. Sorry, a student stepped in and I got sidetracked. Okay, nitrate, because that 8 ending tells me it's a polyatomic, NO3. When I cross my charges, I can see they don't cancel. So when I bring them down, I end up with Hg, NO3 and 2. Because that 2 needs to apply to the whole polyatomic, that's going to go in parentheses. My other reactant is potassium iodide. Potassium is K plus 1. Iodide comes from iodine minus 1. So this one's easy, Ki. I can see I need to figure out what mercury 2 iodide is. So mercury is still plus 2. Iodide is iodine minus 1. So again, you'll notice I already have this information from over here. I'm just recrossing it with our new substance. I get HgI2. And then we have potassium nitrate, potassium and nitrate. So potassium's plus 1, nitrate's minus 1. Plus 1, minus 1, no parentheses needed because I did not bring anything new down. So now I can start putting this into an actual equation. It says that mercury 2 nitrate solution reacts with potassium iodide. So I know these are my reactants. It also says solution. So I know the state of matter. When it's a solution, it's in the aqueous state. It means it was dissolved in water. My second reactant, potassium iodide, same thing. It was dissolved in water. To give, so forms mercury 2 iodide, so the HgI2, and it says the word precipitate. We know what precipitates are. It's just been a minute. That is a solid. So if you want, you can write this word precipitate up in your table up above with solid if you want to write that down. And then we have potassium nitrate solution. Okay. My recommendation is if you have a polyatomic, start with that for balancing. I can see I have 2 nitrates here and only 1. Coefficient of 2 fixes that and gives me 2 potassium. Reactant side needs a coefficient of 2, but that gives me 2 iodine, which I already have. So my mercury are balanced with 1 and 1. Nitrates are balanced with 2 and 2. 2 potassium, 2 potassium, 2 iodine, 2 iodine. As a reminder for reaction type, I can see both reactants are compounds, and what really took place here was an exchange between the potassium and the mercury. This is a double replacement reaction. Okay. Looking at example C then, we're going to change things up. So again, I'm going to move my camera, so give me just 1 second. Okay. It says heating solid potassium chlorate. Notice that ending. And it tells us in the presence of manganese dioxide catalyst. So everything here tells me A, I have a catalyst and I only have one reactant, this potassium chlorate. Again, if you use your periodic table and polyatomic list, you find potassium is a +1 and chlorate is the polyatomic ClO3 -1. So when you cross your charges, you do not introduce any new subscripts, therefore parentheses is not needed. Potassium chloride, well, potassium is +1. Chloride is chlorine -1, KCl. And then the last thing is oxygen gas. Well, it's just oxygen on its own. Oxygen is Hoffman-Kleiber. Oxygen is O2. I can then go ahead and put that in equation form. So I know that I start with this potassium chlorate, and I know that it was heated, and it had a catalyst. So my arrow is going to have two things. Doesn't matter what order. So we're going to put the delta symbol for heating, and that manganese dioxide, MnO2, is the formula there. It makes two things. Potassium chloride, it is a solid. I left that off. I don't expect you to know that. And I have oxygen, which is a gas. When I start looking at the balancing of this reaction, potassium is balanced, chlorine is balanced, oxygen are not. I cannot multiply by 2 to get to 3. That's a whole number. You can use the fraction form if you want. So I'm going to go with 6. To get 6 on each side, I need to multiply reactants by 2, products by 3. That changes this to 2, and that's a balanced reaction. I can see I start with one reactant, end with multiple products. That tells me this is a decomposition reaction. Okay. Last example then. In this last example, this one's probably the trickiest one with a few things to know. So it says in lighters, liquid butane, so C4H10, because that is an organic molecule. I do not expect you to know organic naming. We never learned it. So that's why I give you that it's C4H10. But I do give you that it's liquid, so L for liquid. Combines with oxygen. Oxygen is a gas at room temperature, and it produces CO2 and water. So I didn't do the side thing of showing formulas because most of these formulas are easy to rattle off, and we didn't need to cross charges. The one thing is carbon dioxide is a gas at room temperature, and the word vapor means that it's a gas as well. So I'm going to ask this question opposite than the other ones. This reaction type is a combustion reaction. By knowing that, that is going to help us balance. Combustion, again, is using the choo-choo train method. So CHO, CHO. The other thing that's going to make things make or break with balancing is when we balance a combustion reaction, notice here that the number of carbon is an even number. So there's a trick. Anytime you go to balance and your carbon is even, start by placing a 2 here. You're not going to see the importance right away, but later on it will be important. Now let's start counting. So looking at that with a 2, that means my reactant side has 8 carbons, and I have 20 hydrogens and 2 oxygen. Comparing it to the product side, I have 1 carbon, 2 hydrogens, and in total, adding that 2 and 1 up together, 3 oxygen. So 1, 2, 3. Okay. Start by balancing the carbon. Carbon, we need 8. So on the reactant side, only a coefficient of 8 will work there. When we go to update, you have to be careful. That 8 applies only to the oxygen found within the carbon dioxide. So 8 times 2 I know is 16. Currently, I have 1 oxygen in the water. So right now there is 17 oxygen present on the product side. Move on to hydrogen. Going through the choo-choo method, we have 20 hydrogens. So that means to get 20 on the product side, I'm going to place a 10 here. When I go to update, I've got 20. So my hydrogen and carbon are good. Again, when I update, that 10 does not apply here. So I still have 16 oxygen. 10 times 1, I have 10 oxygen. So when I add those up to get my grand total, I have 16 and 10 to sum up gives me 26. So then my product side is good. I need to finish out my reactant side, oxygen. So what times 2 will get me 26? A coefficient of 13 will. Okay. So what I was looking for here is, again, because of this number of carbon being even, starting out with a 2 there fixes the hydrogen. Initially, if you wouldn't have doubled it, you would have ended up putting a 5 here, and you would have ended up with 5, and you would essentially have an odd number of oxygen. So the trick with combustion is try doubling your hydrocarbon. You can always double every single reaction that's a combustion reaction and then simplify it later on. So again, it's kind of up to you with combustion if you double all of them or if you double only those that are even and then simplify if it wasn't necessary. If you are lost, stuck, confused, come in and see me, ask for help, and definitely ask for clarification if there was any questions on where I got things from in the notes.